Welcome to G Fun Facts Online. In the silent, vast emptiness of space, astronomers have detected a pulse. Not a radio signal, but something far more fundamental: the rhythmic heartbeat of a newborn star. This discovery is completely rewriting the story of how suns are born. Forget the old idea of a slow, serene process. The birth of a star is a dramatic, violent saga of cosmic feasting and furious eruption. Today, we're exploring the story of these stellar heartbeats. For decades, the standard picture of star formation was peaceful. Imagine a vast, cold cloud of gas and dust slowly collapsing under its own gravity. At the center, a baby star, or protostar, would form, steadily sipping material from a surrounding disk for millions of years until it grew hot enough to ignite. It was a picture of tranquil, continuous growth. But recent observations have shattered that image. We now know that protostars are not steady eaters, they are binge eaters. They go through dramatic growth spurts, gorging on huge amounts of gas and dust in violent events that cause them to brighten spectacularly. These outbursts, which can recur with a discernible rhythm, are the heartbeat of a newborn star. They are a powerful pulse that sends shockwaves through the entire stellar nursery. One of the most compelling examples is a young star named V1647 Orionis, located 1,300 light-years away in the Orion constellation. This infant star gave astronomers a front-row seat to its dramatic childhood. It first erupted in 2004, suddenly lighting up the surrounding gas and dust. It faded 2 years later, only to roar back to life in 2008, and it has remained bright ever since. Using a trio of X-ray space telescopes, NASA's Chandra, Japan's Suzaku, and the European XMM Newton, scientists peered through the dense veil of gas cloaking the protostar. What they found was the unmistakable signature of a beating heart. The star was spinning at a dizzying pace, completing a full rotation in just 1 day. That's about 30 times faster than our own sun. This frantic rotation was made visible by 2 searingly hot spots on the star's surface, located on opposite sides and thousands of times hotter than the rest of the star. These are the impact points where material, funneled from the surrounding disk by powerful magnetic fields, crashes onto the protostar. As the star spins, these hotspots rotate in and out of our line of sight, causing the star's X-ray brightness to fluctuate with a regular, clock-like period. It was one of the first times the spin of such a young protostar had ever been directly measured. More importantly, it captured a star at a critical, violent phase of its life, rotating so fast as it gorges on material that it's on the verge of tearing itself apart. This heartbeat isn't just the star's spin, it's directly linked to the chaotic way young stars feed. The engine behind this entire process is a phenomenon called episodic accretion. The journey from a diffuse cloud to a shining star is a battle against physics, specifically the conservation of angular momentum. Think of an ice skater pulling in their arms to spin faster. As a gas cloud collapses, it also spins faster. This rotation prevents a lot of the material from falling directly onto the protostar. Instead, the material flattens into a rotating structure around the star called an accretion disk. For a long time, we thought material flowed smoothly from this disk onto the star, like water gently spiraling down a drain. But that model had problems. It couldn't explain why young stars often appear dimmer than they should, or why they blast out powerful jets of material. Episodic accretion provides the answer. In this model, the disk doesn't feed the star continuously. Instead, material builds up in the disk over long periods, creating a cosmic traffic jam. Gravitational and magnetic forces become unstable until a critical point is reached, and the dam breaks. A massive avalanche of gas and dust is suddenly released and funneled onto the protostar. This triggers a spectacular outburst, causing the star's brightness to increase by hundreds or even thousands of times. The heartbeat is the cycle of these dramatic feeding frenzies, followed by long periods of quiet, Several mechanisms can trigger these bursts. In the cold, outer parts of the disk, gravity can cause the disk to clump into dense spiral arms that migrate inward, eventually crashing into the star. In other cases, temperature changes can cause a runaway effect, dramatically increasing the rate at which material flows inward. The interplay between magnetic fields and the disk's rotation can also create turbulence, allowing material to fall toward the star in sudden dumps. Sometimes, the gravitational pull of a companion star, or even a large, newly formed planet, can disrupt the disk, triggering an outburst with each close pass. These outbursts are the solution to the star's angular momentum problem. As the protostar gains mass, it also launches powerful jets that carry excess angular momentum away from the system. This allows the star to keep growing without spinning itself into oblivion. The heartbeat, therefore, is the regulatory mechanism that allows a star to be born at all. And this isn't a rare occurrence. V1647 Orionis is not an isolated case. Astronomers are finding that this outburst-driven growth is a fundamental part of how all stars, big and small, are formed. In fact, these events are so common they have their own classifications, like FU Orionis objects for long, dramatic outbursts, and EX Lupi objects for shorter, repetitive ones. This model has been especially crucial for solving a major puzzle, the formation of the most massive stars, those behemoths more than 8 times the mass of our Sun. The intense radiation from such a large, growing star should be powerful enough to blow away its own fuel supply, choking off its growth. But episodic accretion solves this. If the massive protostar grows through a series of short, intense bursts, it can pack on mass rapidly during the outburst. Then, during the long, quiet periods in between, its surrounding disk can recover and stabilize, allowing the star to eventually grow to its immense size. A striking example was found in the Cat's Paw Nebula, 500 light-years away. Astronomers were monitoring a baby star cluster and compared observations taken years apart. They found that one of the protostars had suddenly become nearly 100 times brighter. It had undergone a massive accretion outburst, triggered when a clump of gas larger than our entire solar system was suddenly dumped onto it. This is clear evidence that star formation is not a smooth, continuous process, but a sequence of dynamic, violent events. Uncovering these faint, rhythmic pulses is one of the greatest challenges in modern astronomy. These stellar nurseries are hidden inside dense clouds opaque to visible light. This means astronomers must use an entire arsenal of telescopes that can see in other wavelengths, from X-rays to radio waves. X-ray observatories like Chandra can pierce through the dust to see the hottest, most violent regions where material crashes onto the star's surface. This is how we measure the star's rotation and see the heartbeat pulse. Infrared and sub-millimeter telescopes, like the incredible ALMA array in Chile, are revolutionary. They can see the cold dust and gas of the accretion disk itself. By comparing infrared images taken years apart, astronomers can spot an outburst in action as the surrounding dust heats up and glows brightly. Radio telescopes, like the Very Large Array, are essential for tracing the powerful jets and outflows launched during these events. By combining data from all these facilities, astronomers can piece together the complete story of a stellar heartbeat, from the disk to the accretion avalanche to the final eruption and outflow. So why does all this matter? The discovery of the stellar heartbeat isn't just a cool fact. It fundamentally revises our theories of how both stars and planets are born. First, it solves the luminosity problem, the long-standing mystery of why young stars appear dimmer than theory predicted. They aren't always dim, they just spend most of their time in a quiet state between bright feeding frenzies. Second, as we've seen, it provides a viable way for massive stars to form. But perhaps the most exciting implication is for the birth of planets. The protoplanetary disk isn't just fuel for the star, it's the raw material for planets. A powerful outburst from the central star would be a cataclysmic event for a fledgling solar system. The sudden flash of heat and radiation can vaporize materials like water, ice, and organic molecules, fundamentally altering the chemistry of the disk where planets form. The force of the outburst can carve out huge cavities, disrupt the orbits of baby planets, or even blow away the material needed to form them. Paradoxically, the shock waves could also trigger the formation of planets by compressing gas and dust, kickstarting their collapse. Understanding the frequency and intensity of these heartbeats is therefore crucial for understanding the conditions under which planets, including potentially habitable ones like Earth, can form. Did our own sun go through such violent outbursts in its youth? And how did that shape our solar system? The image of a newborn star is no longer a serene nativity scene. It's a portrait of cosmic violence, of a ravenous infant whose frantic beating heart sends shockwaves through its cradle. By listening to this cosmic heartbeat, we are not just witnessing the birth of a star, we are gaining a deeper understanding of our own cosmic origins. Thanks for listening to G Fun Facts Online.